A compact fluorescent lamp, also called compact fluorescent light, energy-saving light, and compact fluorescent tube, is a fluorescent lamp designed to replace an incandescent lamp. Some types fit into light fixtures formerly used for incandescent lamps. The lamps use a tube which is curved or folded to fit into the space of an incandescent bulb, and a compact electronic ballast in the base of the lamp. Compared to general service incandescent lamps giving the same amount of visible light, CFLs use 1/5 to 1/3 the electric power, and last 8 to 15 times longer. A CFL has a higher purchase price than an incandescent lamp, but can save over 5 times its purchase price in electricity costs over the lamp's lifetime. Like all fluorescent lamps, CFLs contain toxic mercury which complicates their disposal. In many countries, governments have established recycling schemes for CFLs and glass generally. The principle of operation in a CFL bulb remains the same as in other fluorescent lighting. Electrons that are bound to mercury atoms are excited to states where they will radiate ultraviolet light as they return to a lower energy level. This emitted ultraviolet light is converted into visible light as it strikes the fluorescent coating on the bulb. CFLs radiate a spectral power distribution that is different from that of incandescent lamps. Improved phosphor formulations have improved the perceived color of the light emitted by CFLs, such that some sources rate the best soft white CFLs as subjectively similar in color to standard incandescent lamps. White LED lamps now compete with CFLs for high-efficiency house lighting. History. The parent to the modern fluorescent lamp was invented in the late 1890s by Peter Cooper Hewitt. The Cooper Hewitt lamps were used for photographic studios and industries. Edmund Gemmer, Friedrich Mayer, and Hans Spanner patented a high-pressure vapor lamp in 1927. George Inman later teamed with General Electric to create a practical fluorescent lamp, sold in 1938 and patented in 1941. Circular and U-shaped lamps were devised to reduce the length of fluorescent light fixtures. The first fluorescent bulb and fixture were displayed to the general public at the 1939 New York World's Fair. The spiral CFL was invented in 1976 by Edward E. Hammer, an engineer with General Electric, in response to the 1973 oil crisis. Although the design met its goals, it would have cost GE about $25 million to build new factories to produce the lamps, and thus the invention was shelved. The design eventually was copied by others. In 1995, helical CFLs, manufactured in China, became commercially available. Since that time, their sales have steadily increased. In 1980, Philips introduced its Model SL, which was a screw-in lamp with integral magnetic ballast. The lamp used a folded T4 tube, stable tricolor phosphors, and a mercury amalgam. This was the first successful screw-in replacement for an incandescent lamp. In 1985, Osram started selling its Model EL lamp, which was the first CFL to include an electronic ballast. Development of fluorescent lamps that could fit in the same volume as comparable incandescent lamps required the development of new, high-efficacy phosphors that could withstand more power per unit area than the phosphors used in older, larger fluorescent tubes. Design. There are two types of CFLs, integrated and non-integrated lamps. Integrated lamps combine the tube and ballast in a single unit. These lamps allow consumers to replace incandescent lamps easily with CFLs. Integrated CFLs work well in many standard incandescent light fixtures, reducing the cost of converting to fluorescent. Three-way lamp bulbs and dimmable models with standard bases are available. Non-integrated CFLs have the ballast permanently installed in the luminaire, and only the lamp bulb is usually changed at its end of life. Since the ballasts are placed in the light fixture, they are larger and last longer compared to the integrated ones, and they don't need to be replaced when the bulb reaches its end of life. Non-integrated CFL housings can be both more expensive and sophisticated. They have two types of tubes, a bi-pin tube designed for conventional ballast, and a quad-pin tube designed for an electronic ballast or a conventional ballast with an external starter. A bi-pin tube contains an integrated starter, which obviates the need for external heating pins but causes incompatibility with electronic ballasts. CFLs have two main components, a magnetic or electronic ballast and a gas-filled tube. Replacement of magnetic ballasts with electronic ballasts has removed most of the flickering and slow starting traditionally associated with fluorescent lighting, and has allowed the development of smaller lamps directly interchangeable with more sizes of incandescent bulb. Electronic ballasts contain a small circuit board with rectifiers, a filter capacitor and usually two switching transistors. The incoming AC current is first rectified to DC, then converted to high-frequency AC by the transistors, connected as a resonant series DC to AC inverter. The resulting high frequency is applied to the lamp tube. Since the resonant converter tends to stabilize lamp current over a range of input voltages, standard CFLs do not respond well in dimming applications. Special electronic ballasts are required for dimming service. CFL light outputs is roughly proportional to phosphor surface area, and high-output CFLs are often larger than their incandescent equivalents. This means that the CFL may not fit well in existing light fixtures. To fit enough phosphor-coated area within the approximate overall dimensions of an incandescent lamp, standard shapes of CFL tube are a helix with one or more turns, multiple parallel tubes, circular arc, or a butterfly. Some CFLs are labeled not to be run base up, since heat will shorten the ballast's life. Such CFLs are unsuitable for use in pendant lamps and especially unsuitable for recessed light fixtures. CFLs for use in such fixtures are available. Current recommendations for fully enclosed, unventilated light fixtures, are either to use reflector CFLs, cold cathode CFLs or to replace such fixtures with those designed for CFLs. A CFL will thrive in areas that have good airflow, such as in a table lamp. Characteristics, spectrum of light. CFLs emit light from a mix of phosphors inside the bulb, each emitting one band of color. Modern phosphor designs balance the emitted light color, energy efficiency, and cost. Every extra phosphor added to the coating mix improves color rendering but decreases efficiency and increases cost. Good quality consumer CFLs use 3 or 4 phosphors to achieve a white light with a color rendering index of about 80, where the maximum 100 represents the appearance of colors under daylight or a black body. Color temperature can be indicated in kelvins or myods. The color temperature of a light source is the temperature of a black body that has the same chromaticity of the light source. A notional temperature, the correlated color temperature, the temperature of a black body which emits light of a hue which to human color perception most closely matches the light from the lamp, is assigned. A true color temperature is characteristic of black body radiation. A fluorescent lamp may approximate the radiation of a black body at a given temperature, but will not have an identical spectrum. In particular, narrow bands of shorter wavelength radiation are usually present even for lamps of low color temperature. As color temperature increases, the shading of the white light changes from red to yellow to white to blue. Color names used for modern CFLs and other triphosphor lamps vary between manufacturers, unlike the standardized names used with older halophosphate fluorescent lamps. For example, Sylvania's daylight CFLs have a color temperature of 3500 K, while most other lamps called daylight have color temperatures of at least 5000 K. Lifespan, CFLs typically have a rated service life of 6,000 to 15,000 hours, whereas standard incandescent lamps have a service life of 750 or 1,000 hours. However, the actual lifetime of any lamp depends on many factors, including operating voltage, manufacturing defects, exposure to voltage spikes, mechanical shock, frequency of cycling on and off, lamp orientation, and ambient operating temperature, among other factors. The life of a CFL is significantly shorter if it is turned on and off frequently. In the case of a 5-minute on-off cycle, the lifespan of some CFLs may be reduced to that of incandescent light bulbs. The U.S. Energy Star program suggests that fluorescent lamps be left on when leaving a room for less than 15 minutes to mitigate this problem. CFLs produce less light later in their lives than when they are new. The light output decay is exponential, with the fastest losses being soon after the lamp is first used. By the end of their lives, CFLs can be expected to produce 70–80% of their original light output. The response of the human eye to light is logarithmic. One photographic f-stop reduction represents a halving in actual light, but is subjectively quite a small change. A 20–30% reduction over many thousands of hours represents a change of about half an f-stop. So, presuming the illumination provided by the lamp was ample at the beginning of its life, such a difference will be compensated for by the eyes. Fluorescent lamps get dimmer over their lifetime, so what starts out as inadequate luminosity may become inadequate. In one test by the U.S. Department of Energy Star products in 2003–04, 1/4 of tested CFLs no longer met their rated output after 40% of their rated service life. Energy efficiency. Because the eye's sensitivity changes with the wavelength, the output of lamps is commonly measured in lumens, a measure of the power of light as perceived by human eye. The luminous efficacy of lamps is the number of lumens produced for each watt of electrical power used. The luminous efficacy of a typical CFL is 50–70 lumens per watt and that of a typical incandescent lamp is 10–17 lumina per watt. Compared to a theoretical 100% efficient lamp, CFL lamps have lighting efficiency ranges of 7–10%, versus 1.5–2.5% for incandescents. Because of their higher efficacy, CFLs use between 1/7 and 1/3 of the power of equivalent incandescent lamps. 50–70% of the world's total lighting market sales were incandescent in 2010. Replacing all inefficient lighting with CFLs would save 409 terawatt-hours per year, 2.5% of the world's electricity consumption. In the U.S., it is estimated that replacing all the incandescents would save 80 TWh yearly. Since CFLs use much less energy than incandescent lamps, a phase-out of ILs would result in less carbon dioxide, CO2, being emitted into the atmosphere. Exchanging ILs for efficient CFLs on a global scale would achieve annual CO2 reductions of 230 mt, more than the combined yearly CO2 emissions of the Netherlands and Portugal. If a building's indoor incandescent lamps are replaced by CFLs, the heat produced due to lighting is significantly reduced. In warm climates or in office or industrial buildings where air conditioning is often required, CFLs reduce the load on the cooling system when compared to the use of incandescent lamps, resulting in savings in electricity in addition to the energy efficiency savings of the lamps themselves. However, in cooler climates in which buildings require heating, the heating system needs to replace the reduced heat from lighting fixtures. In Winnipeg, Canada, it was estimated that CFLs would only generate 17% savings in energy compared to incandescent bulbs, as opposed to the 75% savings that could have been expected without space heating considerations. Cost. While the purchase price of a CFL is typically €3–10 times greater than that of an equivalent incandescent lamp, a CFL lasts €8–15 times longer and uses 2/3 to 3/4 less energy. A U.S. article stated a household that invested $90 in changing 30 fixtures to CFLs would save $440 to $1,500 over the 5-year life of the bulbs, depending on your cost of electricity. Look at your utility bill and imagine a 12% discount to estimate the savings. CFLs are extremely cost-effective in commercial buildings when used to replace incandescent lamps. Using average U.S. commercial electricity and gas rates for 2006, a 2008 article found that replacing each 75W incandescent lamp with a CFL resulted in yearly savings of $22 in energy usage, reduced HVAC cost, and reduced labor to change lamps. The incremental capital investment of $2 per fixture is typically paid back in about 1 month. Savings are greater and payback periods shorter in regions with higher electric rates and, to a lesser extent, also in regions with higher than U.S. average cooling requirements. However, frequent on-off cycling of CFLs greatly reduces their lifespan. CFLs should be avoided in places where lights are frequently turned on and off, as it would increase costs and add to e-waste generation. The current price of CFLs reflects the manufacturing of nearly all CFLs in China, where labor costs less. In September 2010, the Winchester, Virginia, General Electric plant closed, leaving Osramsylvania and the tiny American Light Bulb Manufacturing Incorporated, the last companies to make standard incandescent bulbs in the United States. At that time, Euless Yan, whose Chinese company made the majority of CFLs sold in the United States, said he was interested in building a United States factory to make CFL bulbs, but wanted $12.5 million from the U.S. government to do so. General Electric had considered changing one of its bulb plants to make CFLs, but said that even after a $40 million investment in converting a plant, wage differences would mean costs would be 50% higher. According to an August 2009 newspaper report, some manufacturers claimed that CFLs could be used to replace higher power incandescent lamps than justified by their light output. Equivalent wattage claims can be replaced by comparison of actual light output produced by the lamp, which is measured in lumens and marked on the packaging. Failure. In addition to the wear-out failure modes common to all fluorescent lamps, the electronic ballast may fail, since it has a number of component parts. Ballast failures may be accompanied by discoloration or distortion of the ballast enclosure, odors, or smoke. The lamps are internally protected and are meant to fail safely at the end of their lives. Industry associations are working toward advising consumers of the different failure modes of CFLs compared to incandescent lamps, and to develop lamps with inoffensive failure modes. New North American technical standards aim to eliminate smoke or excess heat at the end of lamp life. Dimming. Only some compact fluorescent lamps are labeled for dimming control. Using a dimmer with a standard CFL is ineffective and can shorten bulb life and void the warranty. Dimmable CFLs are available. The dimmer switch used in conjunction with the dimmable CFL must be matched to its power consumption range. Many dimmers installed for use with incandescent bulbs do not function acceptably below 40 AW, whereas CFL applications commonly draw power in the range 7–20 AW. Dimmable CFLs have been marketed before suitable dimmers are available. The dimming range of CFLs is usually between 20% and 90%, but many modern CFLs have a dimmable range of 2% to 100%, more akin to that of incandescent lights. There are two types of dimmable CFL on the market: standard dimmable CFLs, and switch dimmable CFLs. The latter use a standard light switch, and the on-board electronics chooses the light output level based on the number of times the switch is turned on and off quickly. Dimmable CFLs are not a 100% replacement for incandescent fixtures that are dimmed for mood scenes such as wall sconces in a dining area. Below the 20% limit, the lamp may remain at 20% or flicker, or the starter circuitry may stop and restart. Above 80%, the bulb may operate at 100%. However, recent products have solved these problems so that they perform more like incandescent lamps. Dimmable CFLs are more expensive than standard CFLs due to the additional circuitry. Cold cathode CFLs can be dimmed to low levels, making them popular replacements for incandescent bulbs on dimmer circuits. When a CFL is dimmed, its color temperature stays the same. This is counter to most other light sources where color gets redder as the light source gets dimmer. The Kruithof curve from 1934 described an empirical relationship between intensity and color temperature of visually pleasing light sources. Power factor. The input stage of a CFL is a rectifier, which presents a nonlinear load to the power supply and introduces harmonic distortion on the current drawn from the supply. The use of CFLs in homes has no appreciable effect on power quality, but significant quantities of them in a large facility can have an impact. The power factor of CFLs does not significantly affect their energy-saving benefits for individual consumers, but their use in large numbers such as in commercial applications or across millions of homes in a distribution system could require infrastructure upgrades. In such cases, CFLs with low total harmonic distortion and power factors greater than 0.9 should be selected. Infrared signals. Electronic devices operated by infrared remote control can interpret the infrared light emitted by CFLs as a signal. This may limit the use of CFLs near televisions, radios, remote controls, or mobile phones. Energy Star certified CFLs must meet FCC standards, and so are required to list all known incompatibilities on the package. Outdoor use. CFLs are generally not designed for outdoor use and some will not start in cold weather. CFLs are available with cold weather ballasts, which may be rated to as low as a 23 degrees Celsius. Light outputs in the first few minutes drops at low temperatures. Cold cathode CFLs will start and perform in a wide range of temperatures due to their different design. Starting time: incandescents reach full brightness a fraction of a second after being switched on. As of 2009, CFLs turn on within a second, but many still take time to achieve full brightness. The light color may be slightly different immediately after being turned on. Some CFLs are marketed as instant on, and have no noticeable warm-up period, but others can take up to a minute to reach full brightness, or longer in very cold temperatures. Some that use a mercury amalgam can take up to 3 minutes to reach full output. This and the shorter life of CFLs when turned on and off for short periods may make CFLs less suitable for applications such as motion-activated lighting. Hybrid lamps, combining a halogen lamp with a CFL, are available where warm-up time is unacceptable. The halogen lamp lights immediately, and is switched off once the CFL has reached full brightness. Health and environmental impact. General. According to the European Commission Scientific Committee on Emerging and Newly Identified Health Risks in 2008, CFLs may pose an added health risk due to the ultraviolet and blue light emitted. This radiation could aggravate symptoms in people who already suffer skin conditions that make them exceptionally sensitive to light. The light produced by some single-envelope CFLs at distances of less than 20 cm could lead to ultraviolet exposures approaching the current workplace limit set to protect workers from skin and retinal damage. However, industry sources claim the UV radiation received from CFLs is too small to contribute to skin cancer and the use of double-envelope CFLs largely or entirely mitigates any other risks. Tests have shown that radiation exposure from CFLs is negligible at 150 cm distance from the source. At closer distances, comparisons show that CFLs emit less UVA radiation than incandescent light bulbs. They do, however, emit higher levels of UVB radiation. UVA can penetrate deep into the skin while sufficient levels of UVB can burn superficial layers. Closed CFLs are shielded and emit a lower total UV radiation compared to incandescent or halogen bulbs of a similar wattage. For the average user, UV radiation from indoor lights does not appear to be a concern. For those with skin sensitivity, long-term indoor exposure may be a concern, in which case they may want to use a bulb with lower UV radiation output. There seems to be more variability within bulb types than between them, but the best option is shielded CFLs. A 2012 study comparing cellular health effects of CFL light and incandescent light found statistically significant cell damage in cultures exposed to CFL light. Spectroscopic analysis confirmed the presence of significant UVA and UVC radiation, which the study's authors conjectured was attributable to damage in the bulb's internal phosphor coatings. No cellular damage was observed following exposure to incandescent light of equivalent intensity. The study's authors suggest that the ultraviolet exposure could be limited by the use of double-walled bulbs manufactured with an additional glass covering surrounding the phosphor-coated layer. When the base of the bulb is not made to be flame retardant, as required in the voluntary standard for CFLs, overheating of the electrical components in the bulb may create a fire hazard. Mercury content. CFLs, like all fluorescent lamps, contain mercury as vapor inside the glass tubing. Most CFLs contain 3–5 mg per bulb, with the bulbs labeled eco-friendly containing as little as 1 mg. Because mercury is poisonous, even these small amounts are a concern for landfills and waste incinerators where the mercury from lamps may be released and contribute to air and water pollution. In the U.S., lighting manufacturer members of the National Electrical Manufacturers Association have voluntarily capped the amount of mercury used in CFLs. In the EU the same cap is required by the RoHS law. In areas with coal-fired power stations, the use of CFL saves on mercury emissions when compared to the use of incandescent bulbs. This is due to the reduced electrical power demand, reducing in turn the amount of mercury released by coal as it is burned. In July 2008 the US EPA published a data sheet stating that the net system emission of mercury for CFL lighting was lower than for incandescent lighting of comparable lumen output. This was based on the average rate of mercury emission for US electricity production and average estimated escape of mercury from a CFL put into a landfill. Coal-fired plants also emit other heavy metals, sulfur, and carbon dioxide. In the United States, the U.S. Environmental Protection Agency estimated that if all 270 million CFLs sold in 2007 were sent to landfill sites, around 0.13 metric tons of mercury would be released, 0.1% of all U.S. emissions of mercury. The graph assumes that CFLs last an average of 8,000 hours regardless of manufacturer and premature breakage. In areas where coal is not used to produce energy, the emissions would be less for both types of bulb. Special handling instructions for breakage are not printed on the packaging of household CFL bulbs in many countries. The amount of mercury released by one bulb can temporarily exceed U.S. federal guidelines for chronic exposure. Chronic, however, implies exposure for a significant time, and it remains unclear what the health risks are from short-term exposure to low levels of elemental mercury. Despite following EPA best practice cleanup guidelines on broken CFLs, researchers were unable to remove mercury from carpet, and agitation of the carpet such as by young children plying created localized concentrations as high as 0.025 mg per meter 3 in air close to the carpet, even weeks after the initial breakage. The U.S. Environmental Protection Agency has published best practices for cleanup of broken CFLs, as well as ways to avoid breakage, on its website. It recommends airing out the room and carefully disposing of broken pieces in a jar. A Maine Department of Environmental Protection study of 2008 comparing cleanup methods warns that using plastic bags to store broken CFL bulbs is dangerous because vapors well above safe levels continue to leak from the bags. The EPA and the Maine DEP recommend a sealed glass jar as the best repository for a broken bulb. Recycling. Health and environmental concerns about mercury have prompted many jurisdictions to require spent lamps to be properly disposed of or recycled, rather than being included in the general waste stream sent to landfills. Safe disposal requires storing the bulbs unbroken until they can be processed. In the United States, most states have adopted and currently implement the Federal Universal Waste Rule. Several states, including Vermont, New Hampshire, California, Minnesota, New York, Maine, Connecticut and Rhode Island, have regulations that are more stringent than the federal UWR. Home supply chain stores make free CFL recycling widely available. In the European Union, CFLs are one of many products subject to the WEEE recycling scheme. The retail price includes an amount to pay for recycling, and manufacturers and importers have an obligation to collect and recycle CFLs. According to the Northwest Compact Fluorescent Lamp Recycling Project, because household users in the U.S. Northwest have the option of disposing of these products in the same way they dispose of other solid waste, in Oregon a large majority of household CFLs are going to municipal solid waste. They also note the EPA's estimates for the percentage of fluorescent lamp total mercury released when they are disposed of in the following ways: municipal waste landfill 3.2%, recycling 3%, municipal waste incineration 17.55% and hazardous waste disposal 0.2%. The first step of processing CFLs involves crashing the bulbs in a machine that uses negative pressure ventilation and a mercury-absorbing filter or cold trap to contain mercury vapor. Many municipalities are purchasing such machines. The crushed glass and metal is stored in drums, ready for shipping to recycling factories. Greenhouse gases, in some places, such as Quebec and British Columbia in 2007, central heating for homes was provided mostly by the burning of natural gas, whereas electricity was primarily provided by hydroelectric and nuclear power. An analysis of the impacts of a ban on incandescent light bulbs at the time introduced the notion that in such areas, heat generated by conventional electric light bulbs may have been significantly reducing the release of greenhouse gases from natural gas. Ivanko, Carney, and Wall estimated that if all homes in Quebec were required to switch from bulbs to CFLs, there would be an increase of almost 220,000 tons in CO2 emissions in the province, equivalent to the annual emissions from more than 40,000 automobiles. Such calculations were based on the implicit assumption that changes in power consumption equally affect electricity generation in different types of power stations. That is, the electricity generation mix was assumed to stay unchanged. Hydroelectric and nuclear power stations, in most cases, produce baseload power, or as much electric energy as technically possible, regardless of consumption. Therefore, changes in power consumption may in reality mostly affect the amounts of electricity imported and exported, and thus the amount of power actually generated in other regions, where fossil fuel power plants may dominate. Use and adoption. CFLs are produced for both alternating current and direct current input. DC CFLs are popular for use in recreational vehicles and off-the-grid housing. There are various aid agency initiatives in developing countries to replace kerosene lamps, which have associated health and safety hazards, with CFLs powered by batteries, solar panels or wind generators. CFLs in solar-powered streetlights use solar panels mounted on the pole. Due to the potential to reduce electric consumption and pollution, various organizations have encouraged the adoption of CFLs and other efficient lighting. Efforts range from publicity to encourage awareness, to direct handouts of CFLs to the public. Some electric utilities and local governments have subsidized CFLs or provided them free to customers as a means of reducing electric demand. In the United States, the Program for the Evaluation and Analysis of Residential Lighting was created to be a watchdog program. PEARL has evaluated the performance and Energy Star compliance of more than 150 models of CFL bulbs. The Union Environment Program Global Environment Facility Enlighten initiative has developed the Global Efficient Partnership Program, which focuses on country-led policies and approaches to enable the implementation of energy-efficient lighting, including CFLs, quickly and cost-effectively in developing and emerging countries. In the United States and Canada, the Energy Star program labels lamps that meet a set of standards for efficiency, starting time, life expectancy, color, and consistency of performance. The intent of the program is to reduce consumer concerns due to variable quality of products. Those CFLs with a recent Energy Star certification start in less than 1 second and do not flicker. Energy Star light bulbs for consumers is a resource for finding and comparing Energy Star qualified lamps. There is ongoing work in improving the quality of the light. In the United Kingdom, a similar program is run by the Energy Saving Trust to identify lighting products that meet energy conservation and performance guidelines. The G24 and GU24 socket systems were designed to replace the traditional lamp sockets, so that incandescent bulbs are not installed in fixtures intended for energy-efficient lamps only. Other CFL and lighting technologies, LEDs, solid-state lighting using light-emitting diodes have for some time filled many specialist niches such as traffic lights. White LED lights now compete with CFLs for high-efficiency house lighting. Solid-state lighting has improved over several years. U.S. Department of Energy tests of commercial LED lamps designed to replace incandescent or CFLs showed that average efficacy was about 30 lumen per watt in 2008. In June 2011, the 8 products in the A-line bulb configuration that DOE tested ranged from 50 to 97 lumens per watt, with an average of 62 lumens per watt. The luminous efficacy of currently available LED lamps is similar to that of CFLs, though there have been LED lamps available for purchase with better than 90 lumina per watt overall luminous efficacy at least since early 2012, and higher efficiency LEDs, up to 200 lumina per watt, are under development. Cold cathode fluorescent lamps. The cold cathode fluorescent lamp is a form of CFL. CCFLs use electrodes without a filament. The voltage of CCFLs is about 5 times higher than CFLs, and the current is about 10 times lower. CCFLs have a diameter of about 3 mm. CCFLs were initially used for document scanners and also for backlighting LCD displays, and later manufactured for use as lamps. The efficacy is about half that of CFLs. Their advantages are that they are instant-on, like incandescent lamps, and they have a long life of approximately 50,000 hours. CCFLs are an effective and efficient replacement for lighting that is turned on and off frequently with little extended use. Efficiency comparison, references. External links, The European Lamp Industry's Strategy for Domestic Lighting, Frequently Asked Questions and Answers on Energy-Efficient Lamps, A Technical Description of a Typical CFL Circuit, CFL Intelligence,